Hello everyone. Today let us discuss about some problems on Gauss theorem of electrostatics. This is Gauss law of electrostatics. Already I have explained about Gauss law in my theoretical video. So that is all. Everything I have explained neatly about Gauss theorem and then applications of Gauss law. 3 applications of Gauss law also I have explained in other videos. Now let us solve some numerical problems on Gauss law of electrostatics. I have derived every expression in each and every video about Gauss law. Now what we will do here is we will take those formulas to solve these problems. Now, to solve the problems, first thing is we should know how to solve the problems using a specific formula. What are the formulas which are useful for the particular topic? All those formulas should be on your fingertips. If you don't know the formulas, the first thing is you learn them by opening the book and then close the book, write them again. If you cannot remember them, again write them like that. Five times you write one formula, then at the end of 5 times definitely you will learn them by heart. If anyone has any problem in solving or in learning them, once again you open the book and learn them. If you do like that, definitely at the end of learning them by 10 times, writing them by 10 times, definitely you will be able to solve the problem. Now, what are the important formulas already which we have derived in the previous videos? Now, let us take the important formulas. So, let's take some important formulas for Gauss theorem. So, we have some formulas. So, let me tell you what are the formulas. So, for the first thing is flux. You should know the formula for the flux. What is the formula for the flux? So, first thing is you have to know what is flux. Flux is number of field lines passing through any area. That's given by the Greek letter phi. We are writing subscript E because it is electric flux. That is equal to E bar dot delta S bar. It is a dot product of electric field and area. What is the area vector? The normal to the area is called as the area vector. Because it is a dot product, it comes Es cos theta. This is one formula which you should know. Second thing is, according to Gauss theorem, the flux through any closed surface is equal to Q by epsilon naught, where Q is the total charge enclosed by the surface and epsilon naught is the permittivity. That's a permittivity of the free space. So that is equal to the same thing, that is E bar dot delta S bar. That is for the total area, yes. Now, after that, what are the other problems? Other problems which we have taken, what are the formulas for the other problems? See, we have taken 3 applications of Gauss law in our previous videos. That is flux because of a infinite line of charge, flux because of a infinite plane sheet, and flux because of a spherical shell. Like that, different derivations we have done. So let's take some formulas which are useful to solve them. So what are the formulas which are related to that? That is flux due to a long straight wire that is E is equal to lambda divided by 2 pi epsilon naught r, where lambda is the linear charge density. Lambda is the linear charge density, that is charge per unit length. Charge per unit length. And the next thing is another formula which we have to know is electric field. This formula is the third formula is electric field due to a line of charge. The next formula is electric field due to a infinite sheet, that is sigma by 2 epsilon naught, where sigma is the surface charge density and epsilon naught is the permittivity of the free space. So I think these formulas are enough to solve most of them, and other formulas, if whatever that is required, I will tell you when we are solving the problems. Presently this much is enough to solve these problems which we have taken. And we have also derived the expression for this flux through a spherical shell, that is inside and outside. Inside, electric field is always 0, that we have derived that time. It is there in my previous video. Then that is, if any point is inside, that it is almost equal to 0. If any point is on the outside of them, then electric field is equal to 1 by 4 pi epsilon naught q by r square, where r is the distance of the point from the center that is greater than the radius of the spherical shell. And if you can see, if it is exactly on the surface of the spherical shell, it is 1 by 4 pi epsilon naught q by capital R square, where capital R is the radius, if it is exactly at the on the surface. So this is for inside, this is for outside, and this is exactly at the surface. So these three formulas can also be used in our numericals. Then let's come to the first one. The first problem which we have taken here is, please see this problem. So this is the problem I am taking now. A positive charge of 17.7 microcoulombs is placed at the center of a hollow sphere of radius 0.5 meters. Calculate the flux density through the surface of the sphere. It's a simple problem. Whenever the problem is given, first let us write whatever that is given in the problem. What they have given in the problem is charge. What is the charge they have given? So that in the first problem, the charge they have given, Q is equal to 17.7 microcoulombs, that is equal to, micro means 10 to the power of minus 6, 17.7 into 10 to the power of minus 6 coulombs, that is what they have given. And this charge is placed inside a hollow sphere. Hollow sphere means just like a ball shape. Inside the charge Q is kept, and the radius of that is 0.5 meters. That means radius of the spherical shell or sphere is 0.5 meters. Then what is the flux density? So this formula which we have to use is flux is equal to, you have to use this formula, phi E is equal to Q by epsilon naught. This is the formula which we have to use now. So let's use that formula. That is, flux phi E is equal to Q by epsilon naught, that is 17.7 into 10 to the power of minus 6, and then divided by epsilon naught value 8.85 into 10 to the power of minus 12. Okay, so you can see here, if you multiply 8.85 with 2, you will get 2 5s are 10, 2 8s are 16 plus 1 17, and then 2 8s are 16 plus 1 17. So exactly you will get 7.70. That means 8.8 will cut it it will cut it 2 times. 1 minute. Yes, I was adjusting these settings. 8.85 will cut it exactly 2 times, and that will become this 10 to the power of minus 12. When it goes to the numerator, it becomes plus 12. So you will get 2 into 10 to the power of 2 into 10 to the power of 6. That is flux units are Newton meter square per coulomb. Newton meter square per coulomb. This is only for the calculation purpose I have written here, so you can ignore it. Just I am doing the calculation, so I wrote it, and don't get confused. That is 2 into 10 to the power of 6 Newton meter square per coulomb. Now they have asked for flux density. So flux density means total flux by total area. Flux density means total flux by total area. So flux density is equal to total flux and divided by area. And flux we calculated just now, 2 into 10 to the power of 6. Area means it is a spherical shell. Therefore 4 pi r square, that is 4 pi. R means radius 0.5 square, and once you simplify you will get 6.4 into 10 to the power of 5 Newton per coulomb. I am not doing much calculations here because it will take quite a long time for this YouTube. Therefore this is our answer. The flux density, what we got now is equal to 6.4 into 10 to the power of 5 Newton coulomb to the power of minus 1. So this is our answer. This is how we have solved the first numerical. Now let's continue with the second numerical. Let's go for the second numerical without wasting much time. So this is the second numerical. So we will solve this one. Calculate the electric flux through each of the 6 faces of a closed cube of length L if a charge Q is placed at its center. So the question is, there is a cube. So in that cube, that is kept, a charge is kept at the center of a cube. So like this, there is a cube, and then I'm not drawing completely neatly. So now there is a charge. The charge is kept somewhere inside this one cube. Then the flux will go from all the surfaces, that is top surface, bottom surface, right surface, left surface, back surface, and then front surface. That is 6. This is 5. So 6 surfaces the flux is passing through. Therefore, what will be the answer now? Flux through 6 surfaces is equal to totally for all the surfaces it is equal to Q by epsilon naught. The charge is placed at the center. So the flux is passing through 6 surfaces. So total flux is equal to Q by epsilon naught for the full cube, that is for the whole cube, that means for the 6 surfaces. But in the question they asked what is the flux, for each of the surface. That's what they have asked. What is the flux for through each of the 6 faces? This is what they have asked. So in this case what we have to do now is we have to divide with 6. We have to divide with 6 because they asked us for one surface. Therefore let's take flux through each surface is equal to Q by epsilon naught and 1 by 6, because we have to divide. Therefore the answer is phi E is equal to Q by 6 epsilon naught. So this is the answer for this second question which we have taken. That is, we have to calculate the flux for each and every surface. That means total flux divided by 6 will give you the answer. So this is the second question which we have seen now. Now let's see the third question. Let us see the third question now. So this is the third question. An infinitely positively charged wire has a linear charge density lambda per coulomb per meter. An electron is revolving around the wire as its center with a constant velocity in a circular plane perpendicular to the wire. Deduce the expression for its kinetic energy. Deduce the expression for its kinetic energy. So they can also ask it in such a way. They can give the options like the kinetic energy of the electron is option A, option B, C, D, like that. Multiple choice they can give. In that case, you should, instead of derive, nowadays they are asking like multiple choice questions. The correct answer may be in one of this A, B, C, D options. So in that case, how to solve that problem? So for this, which formula will be useful? Because they said it is a wire and then the linear charge density, then the linear charge density is lambda coulombs per meter. This is a wire. So let us see what is the formula related to the wire. So when you see the formula related to the wire is this one. This is the formula related to the wire. This is the derivation which we have done earlier. It is there already in my YouTube videos. So this is the one. Then in that case, let us use that formula and try to solve this problem. So let's go and try to solve this problem. That is problem number 3. Problem number 3. So what they have given, an infinitely long positively charged wire is there. And what is happening here? There is an electron. There is an electron. So how this electron is revolving? The electron is revolving around the wire like this in a circular way. The center of that circular path is through the wire. And this wire has a surface charge density. It has a surface charge density that is equal to lambda that is equal to lambda coulomb per meter. Linear charge density. I'm sorry. That is the linear charge density is lambda coulomb per meter. Then what we have to find? It's moving with a constant velocity. So let us assume the V is the velocity of this electron which is revolving. Then what we have to find? Kinetic energy of the electron. So if you see the electrostatic force exerted by the line of charge on the electron, it provides the centripetal force for the revolution of electron. We all know whenever something is moving in a circular way, in a circular orbit or in a circular path, it possesses the one force is it possesses kinetic energy, and one force is acting towards the center of the circular path, that is called as the centripetal force. Now how can that centripetal force comes this how can the centripetal force can be acted on that? So that centripetal force is given by the force exerted by the electric field. In the previous video on the numericals of electrostatic force, I have shown you the relationship between electric field and force. E is equal to F by Q. Now it is an electron, therefore charge of the electron is E. Therefore you can say the force is equal to E into E. This is the electrostatic force exerted by the line of charge on the electron. This is the force. This force provides the centripetal force. We all know the formula for the centripetal force, that is equal to mv square by r, where r is the radius of the orbit. That comes in our previous 11th standard. So now let's equate both of them, because the centripetal force is provided by the electrostatic force. Electrostatic force is E into E, that is equal to mv square by r. Now here v is the velocity of the electron, and we all know capital E is equal to lambda by 2 pi epsilon naught r. This formula I wrote earlier and I have shown you here. Here it has yellow color. This is lambda by 2 pi epsilon naught r. So that is what I am applying here in the place of E, that is the electric field. Therefore we will get now E into, in capital E place I am substituting lambda by 2 pi epsilon naught r is equal to mv square by r. So whatever you can cancel now, you can cancel it. That is both the sides. One r and r will be cancelled like that, and then send m to the left side. Then you will get v square is equal to E lambda by 2 pi epsilon naught m. Send m to this side after cancelling r. Then v square is equal to E lambda by 2 pi epsilon naught r. Then what happens now? Kinetic energy of the electron, that is kinetic energy of this electron, is equal to half mv square. Therefore half m, in place of v we will substitute this value, that is this value we will substitute. Then we will substitute that value, that is equal to E lambda by 2 pi epsilon naught m. And then what happens now? M and m cancel. Now finally you will get E lambda 2 into 2 4 pi epsilon naught. This is the kinetic energy of the electron revolving around a line, infinitely long line of charge with the line of charge as its center of the orbit. So this is the third problem which we have solved now. And now, without wasting much time, let's go for the fourth problem. Yes, let's go for the fourth problem. let's take another color for that so that you can understand when you are reading. A large plane sheet of charge having surface charge density 5 into 10 to the power of minus 16, 5 into 10 to the power of minus 16 coulomb per meter square lies in xy plane. Find the electric flux through a circular area of radius 0.1 meter if the normal to the circular area makes an angle 60 degrees with the z-axis. So try to understand the problem. There is a plane sheet of charge of surface charge density 5 into 10 to the power of 5 into 10 to the power of minus 16 coulomb per meter square. Then after that it is lying in xy plane. Then what we have to do, the electric flux through a circular area of radius 0.1 meter if the normal to the circular area makes an angle 60 degrees with the z-axis. Observe carefully, this is in xy plane. But where is this circular area? The circular area is this somewhere, but its normal makes an angle 60 degrees with the z-axis. So now what we can do is, let's start our problem. So for that, which formula is suitable? This is the formula for a surface charge density. This is the formula which we have to use now. Okay, so let's use that formula and proceed. What they have given, let's try to understand. Let us try to understand. There is a plane sheet in the xy plane, and let us say this is in the xy plane. Then another a circular sheet is there, but the normal to that one, it makes an angle 60 degrees with the z-axis. This sheet is in the xy plane. So now that means this one, the circular sheet is making an angle 60 degrees with respect to the direction of the electric field. Circular area is making an angle 60 degrees with respect to the electric field. So let's take whatever they have given in the problem. Let's write them. That is, they have given here surface charge density. Surface charge density they have given, that is sigma is equal to 5 into 10 to the power of minus 16 coulomb per meter square. Then circular area r is equal to 0.1 meter. Then angle it makes is theta is equal to 60 degrees. This sheet is in xy plane. Circular sheet makes an angle 60 degrees with z. That means this electric field is the electric field and the normal to the area, they are separated. If this is the electric field because of the sheet in xy plane, and this is the normal which makes an angle with 60 degrees with the z-axis, then the angle between them is 60 degrees. That is what we have to understand now. Then we have to know the value of epsilon naught. We already know 8.85 into 10 to the power of minus 12 coulomb square per Newton per meter square. And this is what they have given. And just now I have shown you the formula for the plane sheet, and use that one. That is, field due to a plane sheet E is equal to sigma by 2 epsilon naught. Substitute the value of sigma by 2 epsilon naught. that is sigma is equal to sorry, just a minute, sigma is equal to 5 into 10 to the power of minus 16. So let's substitute that. 5 into 10 to the power of minus 16 divided by 2 into epsilon naught, that is 8.85 into 10 to the power of minus 12. This is the E value. Now flux through the area, that is phi E is equal to, that is E delta S cos theta. So that already I have shown you that formula here. Here I have shown you on the top. So this formula I am using here. So this is the formula I am using here. E delta des cos theta, S means area. So here delta S or delta A, whatever it may be, that is delta S or S, whatever it may be, it is nothing but area. So we have to take now E means whatever we have got now, that is 5 into 10 to the power of minus 16, and that is divided by 2 into 8.85 into 10 to the power of minus 12 into delta S. It is a circular area, that means pi r square. Pi r square means delta S is equal to pi r square, because it is circular. Pi means 3.14. R means they have given in the problem as 0.1 meter square into cos theta, that is cos 60. This is what, after simplifying, I am not simplifying here because it will take a long time in the YouTube. So to reduce the time, I am directly writing the value 4.44 into 10 to the power of minus 7, because it is flux. The units are Newton meter square per coulomb. Therefore flux is equal to 4.44 into 10 to the power of minus 7 Newton meter square coulomb to the power of minus 1. So this is the next one which we got now. So this is the next answer which we got for this fourth problem. This is the fourth problem which we have solved now. And then let's see the next problem. This fourth problem is over. Yes, let's go for the fifth problem without wasting much time. Let's take another color for that. This is the fifth problem. A spherical conductor of radius 12 centimeters has a charge of 1.6 into 10 to the power of minus 7 coulombs distributed uniformly over its surface. What is the electric field? 3 points they have given: inside the sphere, just outside the sphere, at a point 18 centimeters from the center of the sphere. So for this, I have already explained you the formulas here. Inside it is 0. I'll write it nicely because this E is something like a line is extra here. Let me write it. E, yes, this is E. E is equal to 0 inside. On the surface it is Q by capital R square. On the surface it is Q by capital R square, exact where capital R is the radius, and outside it is this formula, that is 1 by 4 pi epsilon naught Q by small r square, where small r is the distance from the center. So with the help of these three, we will solve this fifth problem now. Let's finish this fifth problem and then close our video. So let's take the fifth problem. So a spherical conductor of radius 12 centimeters have a surface charge density of 1.6 into 10 to the power of minus 7 coulombs. It has full conductor they have given. It has a charge of 1.6. Then it is distributed uniformly over the surface. That means there is a conductor. There is a conductor, spherical conductor. So on the top of the conductor, on the top of the spherical conductor, the charge is uniformly distributed all over that. Then the radius of that is equal to 12 centimeters. Now let's start our problem. Now let's take Q, that is completely Q over this spherical conductor, is equal to 1.6 into 10 to the power of minus 7 coulombs, and the radius capital R is equal to 12 centimeters, that is 12 into 10 to the power of minus 2 meters, convert it into meters, 0.12 meters. Now, without doing any calculation, we can say the first thing is inside E is equal to 0. Inside E is equal to 0 because already I have shown you here. Here I have shown you E is equal to 0. Then on the just outside the sphere, that means that is at the surface of the sphere, you can see from here, 1 by 4 pi epsilon naught Q by capital R square. So let us do that. Apply that formula. That is exactly just outside the sphere. That is E is equal to 1 by 4 pi epsilon naught Q by capital R square, where capital R is the radius. Here the charge is assumed to be concentrated at the center of the sphere. You can assume that the charge is concentrated at the center of the sphere. Therefore, we all know 1 by 4 pi epsilon naught is equal to 9 into 10 to the power of 9, because we learnt it many times and you applied it many times, used it many times. Charge is equal to 1.6 into 10 to the power of minus 7 coulombs divided by R. R means 1.2 whole square. Then we have to simplify it. We can use like the fourth table and the third table. 4 4s are 16s, 4 3s are 12, like that you can use. That calculations are simple, but I am not showing calculations because to save the time. It may take quite a long time. Once you simplify it, you will get the answer 10 to the power of 5, and the SI units of electric field is Newton per Coulomb. So this is the answer for the electric field. This is the answer for the electric field just outside the surface. This is the answer for that one. Okay, and then so this is the first answer. E is equal to 0 inside. Second answer is we got 10 to the power of 5 Newton per Coulomb. This, I'm going for the question. This is the question. They have asked us, first is inside the sphere, second is just outside the sphere, third is at a point 18 centimeters from that. That means we have to use now the other formula, this one. The second formula, this one you have to use. This one you have to use, where I am putting a tick mark now, that we have to use because this is for outside that one. Now pink tick mark I have put, that formula we have to use now. So let's use that formula now. That is case 3. Sorry, it's yes, case 3, at a distance of r, small r is equal to 18 centimeters, convert it into meters, 10 to the power of minus 2, then it is 0.18 meters. Then simple, that formula we will apply. E is equal to 1 by 4 pi epsilon naught q by r square. 1 by 4 pi epsilon naught is 9 into 10 to the power of 9. Q is 1.6 into 10 to the power of minus 7. And then r means 0.18 whole square. 0.18 whole square. Once again, I'm not showing the calculations because it will take quite a long time. Once you simplify everything, here you will get 4.44 into 10 to the power of 4 Newton per Coulomb. So the final answer E is equal to 4.44 into 10 to the power of 4 Newton Coulomb to the power of minus 1. This is the answer for the case 3 of question number 5. So what we have used here is, we have used a simple Gauss law, that is Gauss theorem of electrostatics, that is the flux through a closed surface is equal to total charge enclosed by the surface divided by epsilon naught, q by epsilon naught. And after that, along with the flux, we use the flux formula. Flux is equal to E bar dot delta S bar, that is another one which we have used. And then after that, which I have derived 3 expressions in my YouTube earlier, that is applications of Gauss theorem. You can see in my theoretical YouTube, you can see all those derivations are there. Now using those derivations, we have 3 formulas. Those 3 formulas, in that today what we have used is, that is electric field due to a straight wire and electric field due to a infinite plane of sheet. This is for a plane sheet. This is for a plane sheet. And the 5th one is for a sphere, that is spherical shell. So that is a long straight wire, lambda by 2 pi epsilon naught, and for a plane sheet, E is equal to sigma by 2 epsilon naught. And for a spherical shell, 3 cases, inside, outside, at the surface. So with these formulas we have completed all these 5 numericals. It's so easy, no? It's very easy to solve the numericals. Only thing is you should know the formulas very well. Okay, learn the formulas very well, and then it's very easy to solve the problems. Okay, all the best. I'll meet you with another video solving few more numericals in another topic. Till then, bye. God bless you all.